Okay, so let me begin by trying to place in perspective where we are at this point of our discussion. So we have the following upper half plane, okay, and this is the upper half plane in the on the complex plane, and then we have the quotient of the upper half plane by the unimodular group, and we have defined a function j tilde which is holomorphic and takes complex values, and we have verified that this function j tilde, this holomorphic function j tilde, goes down to this quotient which we know is a Riemann surface, okay, and it goes down to a function j. So this diagram commutes. In other words, j tilde is invariant for the action of the unimodular group, okay, and so we are trying to show that J is a holomorphic isomorphism in other words, we are trying to show that the natural Riemann surface structure on U mod PSL2Z, namely the set of orbits of the unimodular group on the upper half plane, is the same as the usual complex plane with the natural Riemann surface structure on it, okay, and of course you know that the interpretation for this is also the set of holomorphic isomorphism classes of complex tori. So you think of if you take a tau in the upper half plane, then you take the corresponding complex torus defined by tau, okay, and you take its isomorphism class that corresponds to a unique orbit of PSL2Z, and this is the map that takes tau to its orbit, can also be thought of as the map that takes tau to the holomorphic isomorphism class of the complex torus defined by tau, okay, and of course the whole point is to say that on the set of holomorphic isomorphism classes of complex tori, there is the classification is achieved up to isomorphism by a single invariant, and this is called the J invariant, okay, and so you see we have to show that J, of course J is holomorphic, okay, that can be seen by looking at how the Riemann surface structure on U mod PSL2Z was gotten. In fact we showed that PSL2Z acts properly discontinuously on U, and how this map is a ramified covering, okay, and if you analyze that construction, you can show that because J tilde is holomorphic, J is also holomorphic. So the other thing that one has to show is that J is both injective as well as surjective, because you know a bijective holomorphic map is an isomorphism, okay, which means its inverse is also a holomorphic map. So I have to prove J is injective and surjective, and as I told you, the easier part is to show that J is surjective, and we did that last time by proving that J tilde is surjective, okay. We have proved that J tilde is surjective, which implies J is surjective, okay. That is because this is already a surjective map. This is just the quotient map, okay, sending every point to its orbit. This is just the space of orbits, okay. So usually we put a double arrowhead to denote a surjective map, and I am saying that since J tilde is surjective, so J is also surjective, okay. And of course in the proof of J tilde surjective we essentially made use of the fundamental theorem of algebra, and also namely that the complex numbers are algebraically closed, that is every complex every polynomial in one variable with complex coefficients has all complex roots, all its roots in complex numbers. And of course we also used the fact that the function lambda, the partially modular function lambda, which is not invariant under the whole PSL2Z but invariant under the congruence mod 2 subgroup of PSL2Z, that function does not take the values 0 and 1. We use that also in the proof of the fact that J tilde is surjective, okay. Now the next thing that one has to do is that one has to show that J is injective, okay. So for this I stated the following thing last time, so let me expand on it. So we have, you see, we have so there is this region in the upper half plane, so this is the tau plane, the complex numbers being thought of as the z plane being thought of as a tau plane, and well you take so you take this point which is minus half, this is 0, this is half, and this is 1, this is the point minus 1, and well draw a circle centered at 0, radius 1, okay. So I am going to get I'll only worry about the upper semicircle, okay, and then I draw this line, vertical line passing through minus half and another vertical line passing through half, so I get something like this. So this is the line here, and well, and this is another one here, and the fact is that we called this open region, I mean this open set, which is bounded by this portion of the imaginary axis, this portion of the arc of the unit circle, and this vertical line, we call that as delta, okay, and we call its mirror image by the imaginary axis as delta prime, and then we defined the domain D to be delta, it is just the closure of delta prime union delta and delta prime, the union of the closures, but then you just take out this this line away and then you take out this arc away, okay. So this is this, it is this set minus take out all the yeah, so this line is the set of all tau such that real part of tau is half, okay. So what you do is you take out the set of all tau such that tau in U such that real part of tau is half, and of course the imaginary part of tau is greater than or equal to root 3 by 2, okay. So this point will correspond to a complex cube root of unity, okay. So minus 1 plus I root 3 by 2, so the y coordinate is root 3 by 2, okay. So real part of tau is half, imaginary part of tau is greater than or equal to root 3 by 2, okay. So that is to delete this whole line, okay. So in particular I have also deleted this point, alright, and then I also want to delete this arc of the unit circle, okay, but I would like to retain this point I, okay. So I also take away from this union, okay, I am taking away this, and I am also taking away this union, the other one is this arc which is the set of all e power I theta, with theta varying from theta greater than pi by 2 and lesser than or equal to 2 pi by 3, okay. So but of course one point is common, but anyway let me write that pi by 2 is less than theta is less than or equal to 2 pi by 3, okay. So that amounts to taking away this arc. So finally what I get is, well, this should be real part of tau is minus half, correct, yeah, yes, yeah, I want to take out this line, yeah, thanks. So this is real part of tau is equal to minus half, right, it is this line, it is this ray that I want to take off, okay, yeah, thanks. So you see this is what I want to, so I take this out. So see the net effect is, you know, after I take it out, the if I take the region along with the boundary, see what I'll get is, so let me kind of, you know, make this a dotted arc, okay, so that, and let me also make this dotted, so that, you know, it just to tell you that, well, I've thrown out this this ray and also this arc, okay. So this whole thing is D. So if I draw it, I mean let me draw it once more. The region that I'm worried about is the following. Maybe I draw it, well, maybe I draw it here, doesn't matter. So it's the following region. So this is, well, this is half, this is 1, this is minus half, and this is minus 1, and here is my, and the region I am worried about is, then suppose this is dotted, then I start from here, then I go here, this is not there, okay, and this is my D. This is what D is. This is the region D, okay. This is the region D, and so what I was trying to tell last time is that to prove the injectivity of J is more difficult, okay. So and I said that the first thing is to show injectivity of J tilde, in fact bijectivity of J tilde when restricted to D, okay. So in fact I said I said the following thing, I said we want to prove, so let me write it somewhere here, we want to show that J tilde restricted to D is bijective, okay, among other things, okay. But before I proceed further, let me make a few remarks about what are called as fundamental regions, okay, for mappings and for groups, okay. So let me make a definition. So you see fundamental regions so let me explain what fundamental regions are. So at least in the context that is relevant to us, okay, yeah, so you see, suppose you have x to y, you have a map F is a holomorphic map, be a holomorphic map of Riemann surfaces, suppose it is a holomorphic map of Riemann surfaces, and G is subgroup of the holomorphic automorphisms of the Riemann surface X, okay. So X is a Riemann surface, Y is a Riemann surface, F is a holomorphic mapping, and suppose I have a group G which is certain subgroup of holomorphic automorphisms of the source Riemann surface, okay. and let us assume that f is surjective. So let me put that, sorry, let me put it is surjective, okay. Suppose that f is G invariant. Suppose you have a G invariant map, okay. So that is you see f of G of x is equal to f of x for all x in x and for all for every G in G, okay. So this is saying that f is G invariant is the same as saying that f is constant on G orbits, okay. It is the same as saying f is constant on G orbits, f restricted to every orbit of G is constant, okay. So that is f is f restricted to each orbit of G in X is a constant, okay. Suppose you have a G invariant map, alright. Now of course you know if you have a G invariant map like this, it means that this map factors through the set of orbits, okay. So we have a factorization of maps. So you have x, well x to f is from x to y, and you have got x to x mod g. X mod g is the set of orbits of G in X, okay, and this is the natural map. I put a double arrow because this is just surjection of the set of orbits, and well you have also f is surjective, okay. So the fact that f is constant on orbits means that f goes down to a map like this, okay. So maybe I can call this as f hat if you want, okay. And of course in good situations x mod g could be a Riemann surface. We know already that, you know, for example, if G is acting properly discontinuously on X, then x to x mod G is also a Riemann surface. I mean then x mod G is a Riemann surface, so that x to x mod G, the natural projection, is holomorphic, and then in that case f hat will become also a holomorphic map. But in general if x mod G does not have the structure of a Riemann surface, that is if G does not act nicely, then this is, you just think of it as a set. I am just saying that f is G invariant is the same as saying that f goes down to a map from set theoretic map at least from x mod G, okay. Fine. So given such a map, what is it that we are interested in? We will call by a fundamental region for that map f, what we mean is an open, it is a region in X, namely it consists of an open subset of X, open connected subset, a domain, okay, an open connected subset of X together with a part of the boundary, okay. So it is not open, the interior is open, but you have added a part of the boundary such that f restricted to that set is actually surjective, okay, and you see the translates of that set by G cover all of X, okay. So you see, so in other words you see, so let me write this down. So a subset R of X is called a fundamental region for f if number 1, well, so let me write the following, R consists of R consists of an open connected set together with a part of its boundary that is the first condition. The second condition is the translates of R by G cover X. Okay, so this is the condition that you know every G orbit hits R. Okay, if the translates of R by G cover X, what you are saying is that if you take the orbit of every point in R and take, then you should get all the points of X. That means every orbit essentially has a representative in R, every G orbit in X has a representative in R, and I will put the extra condition that that representative is unique. Okay, so the translates of R by G cover X, and each G orbit of X has a unique representative in R. Okay, of course when I say, if I just say each G orbit of X has a unique representative in R, that already means that the translates of R by G cover X. Okay, but this is more, I want only one representative, right? And the third thing, so this is the first thing. The third thing is F. If I take F and restrict it to R, okay, mind you that R is not a it's not a open set or a closed set, okay, because it's an open set. The interior of R is of course an open set, but there is a part of the boundary that is added. So F restricted to R, for example, you cannot talk about F restricted to R being holomorphic because R is not an open subset. Okay, but the point I want to make is F restricted to R should be injective. It should be injective as well as surjective. Okay, so F restricted to R is both injective and surjective. Okay, so these are the conditions that define what is meant by the fundamental region for a map. Alright, and so you see, let me try to give you examples of this. So if you take examples are, well, number one, you take omega 1, omega 2 are two complex numbers, non-zero complex numbers, such that omega 2 by omega 1 is not a real number. Okay, then you take the lattice L of omega 1 comma omega 2, which is lattice consisting of integral combinations of omega 1 and omega 2. Okay, lattice generated by omega 1 and omega 2, so it is n omega 1 plus m omega 2, where n and m vary over integers. Then you know that I can define a torus using this lattice, namely I take T omega 1 comma omega 2 to be the complex plane modulo this lattice. Okay, so this gives me the complex torus that is defined by omega 1 and omega 2, and so if you now look at this map C to T omega 1 comma omega 2, if you look at this, let me call this map as phi, the natural projection map, the quotient map. Okay, of course you know that this is in fact universal, holomorphic universal covering, with the fundamental group of the torus being identified with the subgroup of Mobius transformations that are given by translations by elements of the lattice. Okay, we of course know that, and the point I want to make is that if you take a portion of the fundamental parallelogram that is generated by omega 1 and omega 2, then that is a fundamental region for this map. Okay, this is a holomorphic map, it is a surjective holomorphic map, and so you see this is a surjective holomorphic map, these two are Riemann surfaces. Okay, the L omega 1 omega 2 can be thought of as a subgroup of holomorphic automorphisms of C, namely translations. Okay, you think of every element here as a translation by that element, and then if you take of course this map this map is constant on orbits because it is actually the quotient map. Okay, so it is invariant under L omega 1 omega 2. Okay, it is constant on orbits by this action. Okay, and for this map the fundamental region is part of the fundamental parallelogram. You throw away two adjacent edges of the fundamental parallelogram and you keep the rest, then that will be a fundamental region. Okay, then the parallelogram defined by edges 1 omega 1 omega 1 plus omega 2 omega 2. So if I draw a diagram, well, so here is, well, if this is omega 1 and well if this is omega 2, then you get this parallelogram here. This is omega 1 plus omega 2. Okay, and you take the parallelogram with edges 0 omega 1 plus omega 2 and omega 2. Okay, and what you do is you take the whole interior, okay, and take for example throw away this edge and this edge. Okay, then that is a fundamental region. Okay, in fact let me say closed parallelogram. The closed parallelogram defined by these edges, defined by the not edges, I should say vertices, defined with vertices. The closed parallelogram defined with vertices, which means I take all the interior of the parallelogram and take also the edges, the boundary. Okay, and then throw out two coterminous edges, namely for example throw out the edge containing this edge and this edge. Okay, minus with minus the edge omega 2 to omega 1 plus omega 2 and omega 1 to omega 1 plus omega 2. Okay, so you take this, so you throw away this, and mind you when you throw away this point is also thrown out. Okay, and you throw away this edge, so this point is also thrown out, and then you take this region. Okay, then this is a fundamental region for the map pi, is a fundamental region for the map pi, because you see first of all you see that every orbit has a unique representative here, that is clear. The second thing is that this map restricted to this is both the map is restricted to that is both injective and surjective, and if I take translates of this by the lattice I will cover the whole complex plane. So all the three conditions are satisfied, so this is a fundamental, that is the reason why it is called the fundamental parallelogram. Okay, but of course you want to really make it a fundamental region, you have to throw out, so obviously one is throwing out this because if I include this then for every point here there is another point there which is another representative, so I throw out this edge so that I get a unique representative for points here, and I throw out this edge so that I get a unique representative for points here, and of course the lattice point will have all the four points will be equivalent under the lattice, so I want only one of them, but I have already thrown out these three, so I get only one. Okay, fine. So now so this is one thing, and you see if you look at, if you go back and if you go back to this so let's go back to this diagram. Let's go back to this diagram. This is also this is a Riemann surface, this is a Riemann surface, and this is a holomorphic map. Okay, and well, you see, of course what is acting on top is PSL2Z, okay, which is a subgroup of holomorphic automorphisms of U, which is all the holomorphic automorphisms of U are PSL2R, and PSL2Z is just a subgroup, is a unimodular subgroup. Okay, and you can, and the fact is, for this map, okay, this is a surjective holomorphic map. For this map, the fundamental region is actually this D. Okay, that is the theorem that we are going to prove. Okay, so I am just trying to rephrase everything in terms of that language. So what I am trying to say is that so the second and third statements I am going to write down are actually claims, we are going to prove them. So the second statement is that the script D is a fundamental region for this quotient map. Okay, 2, we will show that script D is a fundamental region for the quotient map U to U mod PSL2C. Okay, we will prove this. This has to be proved. Okay, I am putting it as an example, but we will have to prove it. Okay, and then so that is so that concerns this map. On the other hand, look at this map. This is also a map between Riemann surfaces. This is also holomorphic and surjective, and again here I have this subgroup PSL2C, which is a subgroup of holomorphic automorphisms of U, and J tilde is PSL2C invariant. Okay, the claim is for J tilde the very same region D is again a fundamental region. Okay, so 3, we will show that D is a fundamental region for J tilde. Okay, and once you prove these two, it will follow immediately that J is surjective. J is an isomorphism. J is, see, because you see so you can think about it for a minute. You see, if there are 2 points here, so first of all J is already surjective, I have to only show injectivity. If I have 2 points here, okay, which are mapped by J to the same point, then I can find 2 representatives there which are mapped by J tilde to the same point, but then those 2 representatives I can move them by PSL2Z into D, because D is a fundamental region and its translates cover the whole upper half plane. Okay, so I will get 2 points here, I will get 2 points here, and with J tilde taking the same value. Okay, but but you see script D is also a fundamental region for J tilde, so J tilde restricted to B, D has to be injective, so that will tell you that those 2 points are actually equal, and that will give me the injectivity of J. Okay, so in that so this is the language we are going to use to prove that actually J is a holomorphic isomorphism. Okay, so fine, so let me having given you this language, let me first go and show the second statement, okay, namely that that script D is a fundamental region for PSL2Z, for the unimodular group. So in this definition I want to say something. I just want to say that, you know, if you apply this definition to the case of a quotient, that is for this quotient map, when this quotient is a Riemann surface, okay, if you get a fundamental region for this map, then that is also called the fundamental region for G. Okay, so the fundamental region for subgroup of holomorphic automorphisms of a Riemann surface is defined, if it exists, it is defined to be the fundamental region for the quotient map with, and then you will have to assume that x mod G is also a Riemann surface and this is a holomorphic map. Okay, so in other words, statement 2 is actually in statement 2 we are actually saying that for PSL2Z script D is a fundamental region. Okay, right. So okay, so let me try to go to that. We now prove script D is a fundamental region for U to U mod PSL2C. Let me call this map as pi, do not confuse this map with the pi in the first example. Okay, let me call this map as pi. Okay, we will prove this. Okay, so so the first thing that I need to show is that of course the first condition is satisfied by D. It is an open connected set together with a part of its boundary. Okay, so D is an open connected set, and what I have included apart from the interior is a part of the boundary, namely this arc of the unit circle followed by this ray. Okay, so it is, so condition 1 is satisfied. It's condition 2 and 3 that I will have to verify. So first thing, let me verify that every orbit of PSL2Z meets script D. I will first prove that, then I will prove that it meets in script D exactly at one point. Okay, we only need to show A1, or let me put Roman letter 1, every PSL2Z orbit in U meets script D. Number 2, every PSL2Z orbit in U meets D exactly at one point. Okay, so of course 2 is in principle, I mean the way I have stated it, 2 is stronger than 1. I mean if I say every PSL2Z orbit in U meets D exactly at one point, it also means that it does meet D at one point. But essentially what I will to prove 2, what I will essentially prove is that if the orbit has 2 points in D, then I will show the 2 points are equal. So this is existence, this is uniqueness. Okay, this is existence, this is uniqueness. So how does one go about proving 1? So for this we will have to again go back and take a small detour into some properties of the lattice. So you see so first of all let us write out what are the conditions that characterize a point of D. Okay, so D is characterized by number 1 mod tau is greater than or equal to 1. Okay, it is it's so this region is on the exterior of the unit circle. Then the second thing is real part of tau lies between minus half and plus half, so it's here. Okay, of course tau is in U, so imaginary part of tau is greater than 0, right. This is all in the upper half plane, and then you see I want to include this arc, okay, and I want to throw out that arc, and I want to throw out this line, okay. So the condition is that slightly a more restrictive condition in part 2, namely that the real part of tau is always greater than minus half, okay. So real part of tau is greater than minus half, which means I could have written 2 and 4 together and said that real part of tau actually lies between, is greater than minus half, but it is less than or equal to half, okay. That throws out this line segment, alright, and then I also want to throw out this arc, okay. So for that I will say that if mod tau is 1, which is the condition for tau to lie on the unit circle, if mod tau is 1, then I will say that real part of tau is greater than or equal to 0, okay. So if mod tau is equal to 1, then real part of tau is greater than or equal to 0, okay. So these are the conditions that characterize when a point tau in the complex plane is in D, alright. And what is it that I have to prove? I will have to prove that give me any point in the, you start with a point tau, now start with a point let us say tau 1, okay, in the upper half plane. I will have to show that in that orbit of that point there is a point in script D, okay. So I have to find a tau 2 which is the translate of which is the image of tau 1 under a PSL2Z element, and such that tau 2 satisfies all these conditions, and I should do this for any tau 1 in U, okay. So starting with tau 1 in U, we seek to produce a tau 2 in D such that tau 2 is equal to tau 2 is the image of tau 1 under a Mobius transformation in PSL2Z, namely a unimodular transformation, okay. This is what you have to do. You start with once you do this, what you are saying is that, so you are just saying that the PSL2Z orbit of tau 1 which contains tau 2 intersects D in tau 2, okay. This is what you have to do. So so the point is that you have to cook up this suitable Mobius transformation, and so that the image of tau 1 under that unimodular Mobius transformation is actually equal to tau 2, and that tau 2 lies in script D, okay. Now so to begin with, to do that, so we begin as follows. So the first thing that we do is that this is, so let me say something before I begin. So this is on the same lines of the proof that I gave several lectures ago, when I was trying to show that a discrete Z submodule of C is either 0, or it is generated by a single complex number, non-zero complex number, or it is generated by integer multiples of 2 complex numbers with non-real ratio, okay. I proved this statement long back, okay, and the proof is actually again an analysis of that proof, okay, and using that proof a little, the ideas of that proof a little cleverly, okay. So we said such that mod omega 1 is least positive, okay. So you see So what you do is that you look at that lattice generated by 1 and tau, and you take a member of the lattice which is closest to the origin. Okay, there may be more than one, but you take one of them. Okay, so call omega 1 to be that. Alright, so call this to be omega 1. Then what you do is, now you look at all those elements in the lattice which are not an real multiple of omega 1, namely not an integer multiple of omega 1, and among those choose omega 2 to be the closest one that is closest to the origin. Okay, so omega 2 is equal to n2 plus m2 tau such that omega 2 is not real multiple, of course it has to be integer multiple of omega 1. Okay, and mod omega 2 is least positive. Okay, so this is how I choose omega 1 and omega 2, and now the fact is that if you take the lattice generated by omega 1 and omega 2, then that lattice is exactly the same as L tau. Okay, so what I have done is, I have, instead of taking the basis 1 comma tau for the lattice over Z, I have found a new basis omega 1 comma omega 2 of the same lattice over Z. Okay, so how does one establish that? So the first claim is that the lattice generated by omega 1 and omega 2 is actually the lattice generated by tau. Of course L tau is lattice generated by 1 and tau. Okay, so the first claim is the lattice generated by, so if that is I am saying, if you take all integer linear combinations of omega 1 and omega 2, you will get all integer linear combinations of 1 and tau. Of course L tau is L1 tau. Okay, L1 tau. Okay, so how does one prove this? So what one does is, if Z is a complex number, okay, if Z is a complex number, you see the first thing that you need to notice is that, you know, omega 1 and omega 2, they are not, omega 2 is not a multiple of omega 1 by the very definition, because you are choosing omega 2 among the members in the lattice L tau which are not real multiples of omega 1. So you see omega 2 by omega 1 is a non-real ratio. Okay, so that is already there in the definition here. Okay, so these are two complex numbers, one which is not a real multiple of the other. Therefore these two complex numbers, see, they will form a basis for the complex vector space C over R, over the real numbers. So which means that any complex number can be written as a real linear combination of omega 1 and omega 2. Okay, so since omega 1 and omega 2 have non-real ratio, there exists lambda mu in R such that Z is lambda omega 1 plus mu times omega 2. Okay, you can write any complex number in terms of these two with real coefficients, okay, because they form a basis of complex number of the field C over as a vector space over R. Okay, now in particular if you take for Z and a member of L tau, okay, so if further Z belongs to L of tau, suppose Z is in L of tau, okay, alright, choose lambda tilde and mu tilde integers, okay, so that the distance between lambda tilde and lambda is less than or equal to half, the distance between mu tilde and mu is less than or equal to half. After all, lambda and mu are real numbers, and I am saying choose the closest integer to lambda and call it lambda tilde, okay, and choose the closest integer to mu and call it as mu tilde. Okay, there could be two of them if lambda or mu happens to be midpoint of an integer, an interval with endpoints integers. Okay, fine. So choose this. Now consider z prime to be, well, z minus lambda tilde omega 1 minus mu tilde omega 2. Look at this element. Look at this element. Now you see this element, see z is in L tau, okay, and if you look at all these things, notice that omega 1 is in L tau, omega 2 is in L tau, therefore the lattice generated by omega 1 and omega 2 is certainly in L tau. The hard part, that is the part that needs to be proved, is that L tau is contained inside this. Okay, so this whole quantity, namely z prime, is in L tau. Okay, this is in L tau. Okay, and compute the modulus of z prime. If you compute the modulus of z prime, well, and plug in for z lambda omega 1 plus mu omega 2, so I will get modulus of lambda omega 1 plus mu omega 2 minus lambda tilde omega 1 minus mu tilde omega 2. This is just modulus of lambda minus lambda tilde into omega 1 plus mu minus mu tilde into omega 2, okay, and this is strictly less than modulus of lambda minus lambda tilde into mod omega 1 plus modulus of mu minus mu tilde into mod omega 2. This is actually less than or equal to by triangle inequality, and you know in triangle inequality you will get an equality only when these two are one is a real multiple of the other, okay, which it is not, omega 1 is not a real multiple of omega 2, okay, they have non-real ratio, therefore it is a strict inequality in the triangle inequality. And well, if you, and you know now mod lambda minus lambda tilde minus lambda is less than or equal to half, so what I will get is this is less than or equal to half mod omega 1 plus half mod omega 2, okay, but you see the way I have chosen, mod omega 1 is the least, okay, and mod omega 2 is greater than or equal to mod omega 1, so this is less than or equal to mod omega 2, because mod omega 1 is less than or equal to mod omega 2, okay, as mod omega 1, okay, by our very choice. So you see, so now if you look at it, I am having an element of L tau, okay, whose this element it is having length, I mean it is having modulus lesser than mod omega 2, okay, therefore this element has to be a integer multiple of it has to be an integer multiple of omega 1. Z prime is an integer multiple of omega 1, that is what it means, okay, and see if, and now go back to this equation. If z prime is an integer multiple of omega 1 and you push z to one side, that will tell you that z is in the lattice generated by omega 1 and omega 2. So I start with a z in L tau and I have established that z is in the lattice generated by by omega 1 and omega 2, okay, therefore this equality holds, okay. So okay, so this essentially shows that L omega 1 comma omega 2 contains L tau, which was the hard part. This is already contained in L tau, that it contains L tau is shown here, so they are equal, so this claim is settled. So what does this tell you? This tells you that omega and omega 2 is another basis for the over Z for the lattice generated by tau. Okay, now keep that in mind, and well, I'll do something so that I can use it for reference later. Let me move all these conditions here. Let me write them here. D is characterized by number 1, imaginary part of tau is positive, mod tau is greater than or equal to 1. Number 2, I will write minus half less than or equal to, strictly less than, real part of tau less than or equal to half, that combines this and this. These two have combined as 1, and there is only one more condition, mod tau equal to 1 implies real part of tau greater than or equal to 0. Okay, so let me put that here. So now let us go back and look at what is written here. So you see omega 1 comma omega 2 is another Z basis for L tau, just like well 1 comma tau. Okay, 1 comma tau is of course a Z basis, and what we have just shown is that omega 1 comma omega 2 is also a Z basis. Now you just write these expressions for omega 1 and omega 2. So you will see omega 2 is m2 tau plus n2, and omega 1 is m1 tau plus n1. You can write it compactly as omega 2 omega 1 in matrix form is equal to m2 n2 m1 n1 tau 1. Okay, you can write it in this form. Okay, and so this should tell you that this matrix, which will this will give you a Z linear map from L tau to L tau. Okay, this matrix will give you a Z linear map from L tau to L tau, okay, which is the same as L tau is the same as L omega 1 omega 2, and this matrix is mapping the basis 1 comma tau to the basis omega 2 comma omega 1. Okay, so the moral of the story is that this matrix is a Z isomorphism. Okay, therefore it is invertible in Z, therefore its determinant is plus or minus 1. Okay, so let me write that here. Hence m2 n2 m1 n1 has a determinant plus or minus 1. Okay, because you see it is a map of L tau to L tau, which is a Z linear map. Okay, and it is taking a basis to another basis. Okay, therefore it is an isomorphism. Okay, so you see you can think about this. Okay, we have used a similar argument earlier, especially we used such an argument to show how in fact we used it to show that if you take tau 1 and tau 2, two different elements of the upper half plane, then the complex tori defined by tau 1 and tau 2 are holomorphically isomorphic if and only if tau 1 can be moved to tau 2 by means of a PSL2Z element. Okay, so it is the same kind of reasoning that you will have to essentially use here. Okay, so this has determinant plus or minus 1. Okay, and well, so what this tells you is that so now what we do is now define tau 2 to be, so you do the following thing. So what you do is you define it as omega 2 by omega 1. Okay, if the determinant above is 1 and you define it as minus omega 2 by omega 1 if the determinant is minus 1. Okay, you define tau 2 in this way. Now the claim is, once you define it like this, then my claim is so already the way we have defined tau 2 is already the image of tau 1 under a PSL2Z element. Okay, so tau 2 so you see tau 2 is actually so tau 2 is in this case, if the determinant is 1, okay, it is well it's m2 tau plus n2 by m1 tau plus n1, okay, with this with the Mobius transformation z going to you know m2 z plus n2 by m1 z plus n1 thought of as an element of PSL2Z. Okay, so this is the first case when the determinant is 1, and or it may be you have to put a minus sign, okay, so that if you put a minus sign then the first row it's only the first row that gets so you have to absorb the minus into the omega 2 or to the omega 1. So if you do that, only one of the rows gets multiplied by minus, therefore the determinant gets multiplied by a minus. So if the determinant is minus 1, you will get plus 1. So it will be, well, minus m2 tau minus n2 by m1 tau plus n1, for example, which is where you know and z going to minus m2 z plus n2 well, this should be minus by m1 z plus n1. This is again in PSL2Z. Okay, so these are the two cases. So what this tells you is that tau 2 is in the PSL2Z orbit of tau 1. Okay, so tau 2 is in the PSL2Z orbit of tau 1. Okay, now the beautiful thing is that tau 2 is almost in D, okay, except that you will have to do a little bit work to very little work has to be done to get all these conditions satisfied. Okay, so I will explain that. So we will have to show tau 2 satisfies most of the conditions for being in script D. So for that I will have to do a translation of so I will have to again go back. So you see it's a little involved. I will have to again go back to the way in which omega 1 and omega 2 were chosen. Okay, so recall that omega 1 and omega 2 were chosen so that well mod omega 1 is less than or equal to mod omega 2. This is a particular condition because we chose mod omega 1 to be the closest point in the lattice defined by tau to the origin, and then we took away all the lattice points on the line that joined omega 1 to the origin, and from the remaining we tried to we took omega 2 to be the closest point to the origin. Okay, so this condition is already satisfied. Then so this is A, and then there are two other conditions. The other condition is the other two conditions are mod omega 2 is less than or equal to modulus of omega 1 plus or minus omega 2. Okay, so this is the second condition. Okay, so well I think this is fairly straightforward, because you see if you take mod omega, if you take omega 1 plus or minus omega 2, that is not a real multiple of omega 1. Okay, so among those which are not a real among those members of the lattice L tau which are not real multiples of omega 1, omega 2 is of the smallest modulus, therefore this holds. Okay, now this is in terms of omega 1 and omega 2. Translate everything in terms of tau 2 with this definition. Okay, so in terms of tau 2, if you translate it, what you will get is the following. you translate everything in terms of tau 2, okay. So this gives a I will call this as well a again, you will get mod tau 2 is greater than or equal to 1 because tau 2 is either plus, it is plus or minus omega 2 by omega 1, okay, and mod tau 2 will be therefore mod omega 2 by mod omega 1 which is greater than or equal to 1. So you see already this condition is satisfied, okay. Then B is, well, these two conditions are equivalent to real modulus of real part of tau less than or equal to half, okay. Okay, which is essentially this condition, okay, except that I need to do something to throw away the case when real part of tau is equal to minus half, okay. So so how does one, I think it is pretty easy to see, essentially probably only yeah, it is just can be seen in the following. So this is tau 2. Well, how do you see this? To see B, write tau 2 as x2 plus I y2, okay, write tau 2 as x2 plus I y2, and then you see B gives well, if you divide throughout by mod omega 1, okay, then you will get mod tau 2 is less than or equal to 1 plus or minus mod tau 2, and now you plug in this. If you plug in this, you will get in fact B is of course equivalent to this, okay, B is equivalent to this, and that is equivalent to, well, I square it, x2 squared plus y2 squared is less than or equal to well, I will get two things. I will get, let me take the plus, then I will get x2 plus 1 the whole squared plus y2 squared, and I will also get x2 squared plus y2 squared is less than or equal to 1 minus x2 the whole squared plus y2 squared, okay. This is what I will get, and of course, you know, if I now expand everything out, see I will get the x2 square and y2 square on both sides will cancel. The first one will give me 2x2 plus it will give me x2 greater than or equal to minus half, the second one will give me x2 less than or equal to half. So this will be equivalent to x2 mod x2 less than or equal to half, and that is, and of course mod x2 is modulus of real part of tau 2. So it is fairly simple that these two translate to these two conditions, okay. So I have got mod, so I got two of these conditions. There is only one problem, namely I will have to ensure what happens when real part of tau is half, and also I have to ensure that the imaginary part of tau is positive. So well, the first thing is, you see the way I have written tau 2 is a PSL2Z translate of an so this I guess was I thought at some point I started with the, did I start with tau 1 or did I start with tau 1, okay. So at some point I missed, so this tau is supposed to be tau 1, okay. So I hope you do not get confused. So you know, I started with a tau in the upper half plane, I mean a tau 1 in the upper half plane, and I was trying to produce a tau 2 in script D which is in the PSL2Z orbit of tau 1, but somehow this tau 1 has changed to tau, so please do not get confused, okay. So this is the tau that I started with in the upper half plane, and I am trying to produce a tau 2, okay, which is in the PSL2Z orbit of this tau and which is in script D. So I am just trying to, so you see, since tau 2 is the image of tau under a PSL2Z element, and since tau is in the upper half plane, the way I have defined it, tau 2 is already in the upper half plane, so imaginary part of tau 2 is automatically greater than 0, okay. Clearly imaginary part of tau 2 is greater than 0, that is I mean that is the reason why we switched we introduced the sign here when the determinant was -1, okay. So so the condition that imaginary part of tau is greater than 0 is now satisfied for tau equal to tau 2, mod tau 2 is also greater than or equal to 1. Now I will have to look at only these two conditions. So you see you do the following thing, okay. So if so let us look at this condition that so let's look at the last condition. If mod tau 2 is 1, okay, if mod tau 2 is 1, consider tau 3 to be -1 by tau 2, okay. That is you are just applying another Mobius transformation, another PSL2Z element on the upper half plane, okay. So you are just applying the transformation Z going to -1 by Z, okay, which is a PSL2Z element. You are just moving it within the upper half plane, and you consider this, okay. Then tau 3 is also in the PSL2Z orbit of tau, because tau 2 is in the PSL2Z orbit of tau, and tau 3 is the image of tau 2 under another PSL2Z element, okay. Therefore tau 3 is also in the PSL2Z orbit of tau, and of course all these conditions satisfied by tau 2 that so far will also be satisfied by tau 3. So we will have well mod tau 3 is equal to 1 by mod tau 2, and of course I assume mod tau 2 is 1, so this is 1 which is greater than or equal to 1, okay. So I have this condition, okay, mod tau 3 is greater than or equal to 1. Of course imaginary part of tau 3 is greater than 0 because it's in tau 3 is in the upper half plane, because tau 2 is in the upper half plane and this is also in the upper half plane then, okay. Imaginary part of tau 3 is positive, and of course you will have also, and you see if you look at the if you calculate the real part of tau 3, you will see that yeah, so you see so real part of tau 3, yeah, you have to just write it out. This is going to be real part of tau 3 is -1 by tau 2, and tau 2 is x2 plus iy2. So if I calculate this I will get real part of, well, multiply and divide by x2 minus iy2, I will get minus x2 plus iy2 by x2 squared plus y2 squared, this is what I will get, and well this is going to be minus of x2 by x2 squared plus y2 squared, and that is minus x2, okay, because x2 squared plus y2 squared is 1, mod tau 2 is 1, and this is going to be minus real part of tau 2, okay, and so you see well, and this is going to be and this has to be greater than or equal to 0, it has to be greater than 0, okay. If so you see I will have to see, okay, so let me explain something. See, for the condition 3 what I will have to do is I will have to worry for the case when mod tau is 1 and real part of tau is negative, okay. So what I do is if mod tau is 1 and let me also and real part of tau 2 is negative, then you do this, then since real part of tau 2 is negative, minus real part of tau 2 will be positive, okay. So I will modify tau 2 by a tau 3 by a PSL2Z element which will satisfy the condition that when mod tau 3 is 1 then the real part of tau 3 is positive, so the third condition is satisfied, okay. you know if tau is I mean the tau 2 that you constructed or the tau 3 that the tau 2 that you constructed, if it was on this line on this ray, then all you had to do is just translate it by 1, and translation by 1 is also a PSL2Z element, okay. So that is all you have to do. So you can ensure therefore that in the given any tau in the upper half plane, there is a representative of its PSL2Z orbit in script D, okay. So probably I should stop here, okay, and in the next lecture what I will try to do is I will try to show that there is only one such representative in script D, okay, and that is what will make script D into a fundamental region for PSL2C, okay. So I will stop here.